Okay, so number 7 on chapter 17. Oh, I got to share screen. My bad.
I say.
I was gonna say like, oh, yeah. Okay, share screen.
I need my chicken nuggies.
Yeah. Yeah. You look more like Joe Exotic over there.
Wow. I just woke up. This is all natural. I didn't put any of my male makeup on. This is all natural.
Mm-hmm. Okay, so course plan. So we're going to go into the chapter 17. La-di-da. Okay, I'm going to open up chapter 18 momentarily. So number 17, number 7 on chapter 17.
Joe Exotic, anybody?
Okay, okay, numbers, pH at equivalence point. Okay. Question review. So, calculate the pH at equivalence point for the titration of methylamine with hydrochloric acid. Okay, so the idea here, at equivalence point, all the base, the weak base is neutralized to form weak acid. And so we're going to have to figure out what is the acid concentration and then work backwards. Because, okay, I'm pulling up paint so I can start working on this. But you're going to have a basic chemical equation. So let's start with it. So with your base, we're starting with a weak base. So a base in water would typically do this. Goes reversibly to pronated base, and so methylamine is doing just that, and OH minus. Now, as we add an acid to this base, so this is a weak base, this is our conjugate weak acid. As we add an acid to that base, we are not having straight up negative hydroxide in there. We're having salt. That's not going to go back at all. So as we neutralize the base with the acid, we're going to have some amount of base and some amount of conjugate acid, and so we're going to have a buffering region. But when acid and base cancel out, we have only this in solution. And with only that in solution, we then have this experience where we have this conjugate acid-base chemistry that occurs with water. So a weak base will be acidic at the equivalence point. A weak base will be acidic at equivalence point. Just like a weak acid will be basic at equivalence point. So how do you tell a weak acid from a strong acid? You look at the pH at equivalence point. A weak acid will be above 7. A strong acid will be at 7. But so it's asking us, what is the amount of H3O under this scenario? What is the amount of H3O under this scenario where I have all BH, all pronated base, and no depronated base? So let's look at that. So, I'm sorry, wrong thing. So it says pH 0.19 molar methylamine with 0.19 molar HCl. Okay, so we have 0.19, 0.19. So, and 0 at initial. When I subtract this, 0.19 goes to 0. Oh shit! Already screwed up. Okay, let me go back. I need to delete that. So from this scenario, we have 0.19 of this, 0.19 of this, and 0 initially. Then as they neutralize, this gets canceled out, and this gets formed. The moles of base we started with will equal the moles of conjugate acid we form. So if we had 4 moles of base, we would generate 4 moles of acid as it gets neutralized, because the conservation of matter. So we're not destroying the base, we are converting it. Just the same way as we would also have 0.19 moles of the salt because of this. But the 0.19 moles of the salt don't mean shit to nobody. We don't care about chloride. The chloride is a neutral salt. So we have, this is the amount of base we would have, or this amount of acid we would have. So we have to calculate what is the pH of a weak acid. So how would we calculate the pH of a weak acid? We would set up the Ka expression. Ka equals hydronium times base over protonated base, which is going to be what, x squared over 0.19. Now the only thing we have to do is calculate what is our Ka. They give us our Kb as being 5 times 10 to the negative 4th. So if Kb is 5 times 10 to the negative 4th, then Ka must be 10 to the negative 14 divided by our Kb, which would give us, negative 14, which would give us 2 times 10 to the negative 11th. Okay, with that in mind, so how would we have done this? We would have said X, which is our hydronium, H plus is equal to the square root of Ka times 0.19. So I got my Ka, I multiply by 0.19, and I take a square root of that. And that would give us the concentration of acid that would be at equilibrium. So that's 1.94, we'll say 1.95 times 10 to the negative 6. 1.95 times 10 to the negative 6. Okay. And then once again, because it's an acid, we take the negative log of that to get the hydronium, the pH. So, and I get 5.71. 5.71. Don't round in. What? What the? What the?
Big brain time.
Okay. 19. Oh God, is it this? Okay. 2 times 10. Okay, the way they word this is stupid, but okay. Oh. 1.9 times 10. Okay, this is probably it. Now the way they do this, yeah, that's it. The way they do this is stupid because they don't make it abundantly clear how they're doing it. So the problem here, 5.71, is a little shy because what's happening is they don't give us a volume, and that's what threw me off, because moles need to cancel out moles. So what does this mean? We need equal amounts of acid and base. When I add equal amounts of acid and base, what's going to happen to the volume? The volume will double. So it doesn't matter if this is 10 mils of acid and 10 mils of base going to 20, or 5 mils of acid and 5 mils of base that go to 10. What's going to happen is the concentration of the acid and the base will be diluted by a factor of 2. So what does that mean? This number is actually going to be divided by 2. So that 0.19 is going to be actually 0.095. 0.095. And so as we calculate this, 0.095, 0.095, and that's going to change this to instead of 1.95, 1.38. It's not a huge change, but it's enough of a change that they'll mark you wrong. It's because when they add this, the way they add this is they're doubling the volume, and so that's going to half the molarity as you double the volume, because it's equal amounts of acid and base neutralizing each other out. So when you take the negative log of 1.38 times 10 to the negative 6, it goes to 5.86 instead of 5.71. Changes by a factor of what? 0.15? But that's enough of a rounding error to mark it all wrong. So the thing to note as you do that one is this is going to be your starting molarity of your weak acid, but you have to divide by 2 because you're diluting with equal amounts of acid and base. Doubling the volume, having that. But then it's just half of that times your Ka, not your Kb, and you square root that, and that'll give you your H plus. From there, we will find your negative log. Check the chat. Wow. What the? Review the chat. Okay. For God's sake, show the damn chat. Hey, look at that. Okay. Well, no, that's not it. That's not what I want at all. Okay. Well, trying to figure out how to make the chat pop up. Okay, well, okay, let's see. Chat. Okay, big. Okay, sorry. Yeah, 16. Someone should be reading the chat to me. 16 from chapter 17. Oh, okay. 16 from chapter 17. We'll go
16 from chapter 17.
a little late now.
You said read the chat.
What at what?
Someone also wanted to know chapter 17, number 8.
Number 8.
Yeah.
We'll do 8 real quick because 8 is really is the one that was like Titration One. So okay. So weak acid is the analyte. So we want to make sure weak acid. You're going to want an indicator of, let's say, phenolphthalein. We can try that. So we're going to just slowly, you look at that, titrate. Whoa, it jumps up. You can keep on playing back and forth. But so around the amount where it jumps, it's about we go, oh, it's about 25. That seems about a safe bet. 25 is where we have the equivalence point. Now, the half equivalence point of a weak acid, the half equivalence point of a weak acid is going to be your pKa. pH equals pKa. So if this is 25, half of that is going to be 12 and a half, which it's kind of hard to read with this shitty graph, but there is that beautiful thing that you can keep on. Oh, I'm going to go all the way back to 12 and a half and just read the number. So that looks close enough to 5. Say 4.995, whatever. I can actually add one more, exactly 5. So pH equals pKa at half equivalence point for a weak acid. For a weak acid. This is true for every weak acid and every weak base. So let's look at a weak base real quick. I'm going to want a different indicator because it's going to jump the other way. But if I add a strong acid, whoop, so we have the same thing. If there is my equivalence point right about there, right about there, 25, then our pH equals pKa at that half equivalence point. So 12 and a half would be at 9 for that weak base. The pKa for that weak base would have been 9. If I did a diprotic, you get a weird thing, a similar thing, but you get 2 jumps. You say, oh, da da da, da da da. In this case, pH equals the pKa for the half equivalence point at 12 and a half. And between 20 and 50, which would be like, what, 37.5, would be the pKa 2 for that guy. So this is not really hard interactive. It's just a kind of neat one that shows what will be seen in lab for the Ka of a weak acid lab. The other one was like 16. Was it number 16?
Yeah.
Yes.
Okay. This one, it's confusing the shit out of everyone, but it really shouldn't be. It is really, really, okay. There are 6 different problems, so you cannot just simply copy someone else. Where the problems change are only in these first 4 statements. Only in these first 4 statements will the problem change and vary. This part will not. This is a description of what types of solids these guys form. Silver, lead, and mercury will form solids with chloride. Bismuth, cadmium, copper, mercury, lead, antimony, tin 2, tin 4 will form acid sulfides. Aluminum, cobalt, chromium, iron, nickel, manganese, zinc will form base sulfides or base hydroxides. Barium, calcium, magnesium, strontium will just form carbonates, and lithium, sodium, potassium, and ammonium will not form any solids at all. So you're getting a test tube with a bunch of metal in it, and you're testing to see what types of compounds do you have. You can only test things for positive or negative. You can't say, at least with this crude test, which one it is. But you can say if there is one, period, or there isn't. So this is one of the problems. If I add dilute HCl, so it's acidified, and there's chloride, and there's a solid formed, means we have one of these guys. One of these guys, silver, mercury, or lead. So one of those guys are present. You cannot say all of these ions were present, but you know at least one of them are present. Then you filter these off. So you take away any mercury 1, lead 2, or silver 1. Then you bubble acid sulfide through. you form a solid. So it means there has to be at least one of these guys. And so you say at least one of these guys. We change it to basic and try again, but no solid this time. So because we have no solid under these conditions, it means we have no iron, no chromium, no cobalt, no aluminum, no nickel, no manganese, no zinc. These guys are definitely not there. So none of these. And finally, I add carbonate, and once again, there is no solid. So it means there's no barium, no calcium, no magnesium, no strontium. So for this particular problem, I'd say 1, 1, none, none. But then I'm left with here. Because these guys are completely soluble, there is no convenient way to test for them. So we only can say these guys are unknown. And that's the only thing that really shouldn't change from problem to problem, is that these guys are going to be unknown because there's not an easy way to test for them to make a solid. So this is what we're looking at. So you may get this version. You may get this version that has solid, solid, no solid, solid. You may get this version, which is solid, no solid, solid, no solid. So you could get any combination, and you're just literally reading these statements, and where there's a solid form, we see proof of at least one ion. Where there's no solids formed, we see no proof of any of the ions. This is something I did in high school. There's actually a dozen different tests. You could split up this guy and test for silver individually, mercury individually, and lead individually. And one reaction that only works with lead versus only works with mercury, where it only works with silver. And you could say, oh, we have silver. Oh, but we don't have lead. But right now, this is just a quick thing. It says, is there any silver, mercury, or lead? Yes, no, maybe so. That's all. It's not supposed to be a hard one. I thought this would be a fun one, but apparently this has caused people untold suffering. I'm sorry. It's really not too bad. Okay. I'm going to stop this meeting, and I'm going to start the next one because we're running out of time. So I will see you in a few minutes. I've got to upgrade this, but we'll worry about that. We'll go and go over one of the strong acid-base titrations in the homework. I think there's only really one, but okay. So whole scheme, predicting precipitation compound. Okay. Oh, geez. I thought I removed that one. Oh, that one's not. That one's okay. That one you don't need to overthink that. Okay. This one is like, yeah. Let's see. I'm just looking at this page. That's a buffer. Okay, so this one's so this is a titration one. So 25 mil sample of 0.3 molar lithium hydroxide is titrated with 0.75 molar HI. It doesn't really matter what you're titrating with. This is number what, like, let me pull it up. Number four on the homework. But like, it doesn't really matter what you're using. The idea is it is a strong acid. It is a strong base. The concentrations don't really matter. You're just calculating this. So they want to know.
You're not screen sharing.
Oh, so yeah. Well, I'll screen share in just a second. Good point. But screen share. Okay, there we go. Screen share. So So the idea here is 25 mils of 0.32 molar lithium hydroxide. So 25 mils of a 0.32 molar strong base is titrated with 0.75 moles of a strong acid. Calculate the initial pH and the pH after 5 mils. Now, the 5 mil part doesn't really matter. If you know how to do it once, you know how to do it at any point. And there's only really 4 points you care about on these. So let's pull this up. So we have base. Let me put base, OH, and acid. 0.75 molar, 0.32 molar, and that.
I think that's the other way around. I think that's the other. I think it's the other way around.
No, I'm pretty sure it's 0.75 molar acid and 0.32 molar base, unless it's 0.23. No, 0.32.
Oh, okay. I had it wrong.
Yeah. Well, but okay. So some of these points will be really, really easy. I'm going to actually do all 4 points, but some of these points are going to be really, really easy. So don't overthink this. There's only 2 parts of this that should be hard. 2 parts of this that should be hard. During titration and after titration. But the first part, the initial point. The initial point is saying, what is the initial pH of solution? So I know this is a bunch of fancy words, but the initial pH of solution is just going to be, we have OH, nothing else, full stop. How would you calculate pH of a OH solution? Well, POH is equal to the negative log of OH. So the first point is just going to be the negative log of 0.32. Going to be POH. The negative log of 0.32 going to be 0.495. And my screen's not letting me write it perfectly as I'd like. So that's POH. Now to calculate pH, you say 14 minus POH. So 14 minus 0.495 is going to be what? 13.505.
Yes.
Yeah, 13.505. Or it might accept 13.51. I don't think it really matters as long as you don't round too unnecessarily. I'm going to put 0.505. Okay. That is an easy one. Don't overthink that. Don't overthink that. Now, how much acid would it take to neutralize this? Well, we'll calculate that in just a second. So during the titration, this is the first hard problem. Step 1, you will calculate the moles of each guy. How do you calculate moles? Don't overthink it. Molarity times volume equals moles. So 0.32 times 25 is 8. Now, for
Wait,
acid,
how do we do this?
molarity times volume. This is GenCam 1. Molarity times volume equals moles.
Okay.
Now, our 0.75 molar acid, we add 5 mils of that. They say that in the problem, 5 mils. That makes that 3.75. So that is step 1. Step 1. Step 2, you cancel out moles with moles. So I cancel out 3.75 acid and 3.75 base. If I have more acid, I cancel out the base. I cancel out the lesser one. 8 minus 3.75 gives us 4.25 base remaining. That is step 2. Step 2. Step 3 is where I got tripped up on the problem last video. I need to calculate my dilution factor. So I add 25 mils of base with 5 mils of acid, making 30 mils total. So 30 mils total, I have to turn this back into molarity. So 4.25 divided by 30 will give us 0.14, we'll say 2. It's 0.1416 repeating. So we'll go in and round. That is step 3. That is the, if you can get through those first 3 steps, that is the hard part. Now, step 4, the last step, is the easy part. What is left? This is OH, 0.142 molar OH. So I take the negative log of 0.142 molar and give us our POH of 0.8477116556. I'm going to 848. Now that's POH. So 14 minus that gives us 13.152. So that's the answer to number 4, at least on my problem. 13.152. Okay. So yes, they rounded.
I'm still confused on how to go from the first answer to the second answer.
The first, this answer?
Yeah.
Okay, that answer is completely unrelated to the second answer.
Okay.
For the first answer, it's literally just we have base, nothing else. There's no neutralization occurring. It's just how do we find the pH of a base?
Yeah, I got my first answer on my own, like before this, but I could never figure out the second.
Well, the second answer, it's all dependent on, you have to do those 3 first steps. You have to do those 3 first steps, which are calculate moles. Step 2, which is neutralize acid with base. Step 3, which is then redilute. So turn moles back into molarity. And how would you do that? You take moles divided by total volume.
Okay.
And then it's, you take the negative log. Now, there's 2 other data points we could take here. They only asked this of us. But there's 2 other data points we could take. The data point at equivalence point, and the data point at after equivalence point. So let's look at that. So hypothetically, let's look at equivalence point. So that 8 isn't going to change. The amount of base we started with will never change. We had 25 mils of base and 0.32 molar base. That's always going to be 8 millimoles. That's never going to change from our initial calculation. But the acid goes up as we add more and more and more. So at equivalence point, we've added 10.67 mils of acid, sorry. So 10.67 mils times our 0.75 would give us approximately 8 millimoles of acid. So at equivalence point, 8 cancels 8. So how much acid do we have? 0. How much base do we have? 0. So when there's no acid and no base, it is neutral. So what is the pH at equivalence point for a strong acid, strong base titration? It's 7. So when the acid and base cancel out at equivalence point, it's always 7 for a strong acid, strong base. Don't overthink it. You try to take the negative log of 0, you're going to have a bad time. For at equivalence point for a strong acid, strong base, it's always 7. You won't even really need to show so much work, is that you can write 7 ipso facto strong acid, strong base. But one last problem. What if I, instead of at equivalence point, just after equivalence point? Let's say instead of 10.67 mils, I chose 12 mils of acid. 12 mils of acid. The amount of base we started with doesn't change, still 8. But now the amount of acid has gone up. So 12 times 0.75 gives us 9 moles of acid. So 0.75 times 12 is 9. Now we subtract out the lower amount. Since we have now more acid than base, the acid gets neutralized by the base, leaving 1 mole of acid left. So that's 1 mole. So that's step 2. Step 3, we have to calculate our dilution. We added 25 mils of base. We have 12 mils of acid. So that's going to be how much volume? 37. So 1 divided by 37 is how much acid we have. That's 0.027. Now, once again, step 4 should be the easy step. Step 4 should be the easy step. We are taking the negative log of this number. Take the negative log of this number. So negative log of this is going to give us pH. Why is this pH and not POH? Because we have more acid left than base. In this problem, we started with base and went to acid, but now we have more acid, and so it's staying acid. So the negative log of this gives us a pH of 0.157. So those are the 4 data points you could take throughout this titration. The first one should not trick you. The third one, the at equivalence point, should not trick you. The ones that will be a challenge will be during and after the equivalence point. During and after. But you break it down into those 4 steps. Turn to moles. Neutralize. It's just like an ice table. We're canceling 2 things out. Redilute. And then H plus to pH or OH minus to POH. So step 4 should always be like, oh, not too bad. But step 1, 2, and 3, yes, they can be a little tricky. And they're even harder, as I said, if we were doing a weak acid or weak base. Which is why I went ahead and skipped that. I said, no, we will not do that this year. We already have enough trouble going through this as is. So, now, is there any more? Okay. Okay, so I'm going to briefly start, at least introduce this new chapter. This new chapter is chemical thermodynamics. It should be a refresh of the thermodynamics that we talked about in general chemistry, except hopefully once we get through the basics of it, it's more or less the easy part. It's not so much the actual like calculating heat transfer, but it's a lot of looking up numbers on tables and find out energy of reactions. So now we'll look at entropy and spontaneity. Essentially, why does randomness happen and why do things happen without any external outside force? And so, but in order to understand this, we have to remember the idea of internal energy, that the energy of a system is a function of work and heat. And then we could write the equation that essentially internal energy is heat plus work. So if the heat is going into, work is going into a system, the energy of the system goes up. If heat is leaving and work is leaving, energy is going down. And we had to remember things like heat of the system versus heat of surroundings. My body could be the energy system and surroundings is the area outside. If outside is hotter than me, heat is going to flow from the outside into me, making my body hotter. If the outdoors is colder than me, then heat is going to be leaving my body and flowing into that. But the big thing we have to remember is the enthalpy of reactions. We calculated how much heat energy would be produced when we made a reaction go. If I burned methane, how much energy could we form? And how did we calculate this? We calculated this through delta H. The reaction is the sum of all the products minus the sum of all the reactants. So you say the products minus reactants. If there's two products, you added both products. If the coefficient was 2, you multiplied by 2. If there's 5 reactants, you would subtract all 5 reactants from the products. And you could use this to find out, is this reaction going to produce energy or absorb energy as it goes? Some reactions produced energy, most in fact did. Some would absorb energy. And so we're going to look at that again. So the first law of thermodynamics, which we kind of covered last semester, was that energy is conserved. Energy can neither be created nor destroyed. And that fit in with the internal energy is heat plus work. If I'm losing my work, it has to be being transferred into something else, like heat. So if I'm running my engine and I'm not getting 100% efficiency out of my engine, it's being lost as heat instead of work. But that first law of thermodynamics does not tell us whether a reaction will happen or not. It just tells us energy is always conserved. So let's define what it means to be spontaneous first. It's not just, whoa, he's wild and crazy guy, he's going to do anything. When we talk about spontaneous and a spontaneous reaction, it's a process that will occur naturally without any outside intervention. I don't have to ask you, when you do the dishes, you're going to do the dishes spontaneously without me needing to nag you. Like in terms of chemistry, say, if I put a rock on the top of a hill, gravity's going to pull it down the hill. We don't need to give it a push. It's going to spontaneously roll down that hill because of the potential energy and gravity. If I mix cream with coffee, I don't have to stir it. It will mix by itself in time. You fart in an elevator, everyone will smell it eventually. You don't need to like waft it around. It's going to happen. Stuff will mix. Energy will flow to the low point. That's always what's going to happen. All these guys are spontaneous reactions. But some spontaneous reactions will depend on temperature. So like, for example, freezing. we can say that water will freeze below 0. That's spontaneous. You put water in a fridge, it will freeze. A refrigerator, the freezer, it will freeze. But if you put water on a counter, it will not freeze unless you're in like Minnesota. It's not going to freeze right there on our desktop right here. Yeah, so maybe up in Canada it's going to freeze if you leave it outside right now. I don't know how cold it is right now.
Hey, now it's actually the snow is melting. About
Okay.
a couple of days ago, though, we had a snowstorm. So like,
yeah. So I mean, it depends on what season you're in, whether this water is going to spontaneously freeze, because it's all temperature dependent. Now, reversible processes will not happen without the reverse process will not happen without intervention. And sometimes these reverse processes are near impossible. This is what's known as a non-spontaneous thing. So I can put a rock and push it back up the hill, but it's not going to roll up that hill without work. I can use a centrifuge to spin out the cream and like separate it by density. Or I can use high heat to maybe remove that. But I mean, I could possibly condense a gas from the air. But these are not things that are going to naturally happen without us putting in outside work. They're not done without outside work. They need an external source of energy. So I'm going to get maybe to the next slide, and that's where we'll end. So the second law of thermodynamics states that any spontaneous process will result in a net increase in entropy of the universe. Now, entropy is a measure of the degree of randomness or disorder in a system. It's much easier to create disorder than it is to create order. If you've ever tried to clean up your room as a child, you know it's a lot easier to make that mess than it was to fix it. Seems like it takes a lot more energy to pick everything up and put it back in its proper place. That's because you have randomness working against you. You knock something off a shelf, you spill your coffee, whatever, it's going to take a lot more energy to clean that up than it did to bump and spill that over. So all this entropy, examples of this, we could have a phase change. When we go from a solid to a liquid, it's more random. Liquid to a gas, it's even more random because gas can bounce all over the place. Anytime we increase in temperature, we're going to get more random, more crazy. When I dissolve a solid into a solution, that's usually more random. If I mix two substances together, like I stir together like red and green Play-Doh, we're not getting that Play-Doh back out. Maybe we're going to make a nice new color. Maybe we'll just make brown Play-Doh. But you mix that together, that's going to be mixed together. That makes more randomness. If I increase a number of particles of gas, all these things will be an increase in entropy. And so we'll talk more about this. We'll talk more about this in the next video, but we'll go ahead and stop that for now. And I will post the next video live, I don't know, maybe tomorrow, whenever I get a chance to take it. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That, well, we're not